Right, today I'm going to be looking at this CrackMe called Confusion. I'll put the link in the description below. But it says it's a Windows binary, it's difficulty 3, and it also mentions some anti-debugging stuff in here, which we can look at. But yeah, so if I download the CrackMe, just run it, see what it looks like. So, do you want to see the rules? Let's see what the rules say. Don't patch it. Find a password and make a keygen. So let's try that. So let's run it again. Continue. Type your username. Fred. Input your password. I don't know. Oh, it's okay. So it asks you for each. So it's kind of like a serial number in 11 parts. So and it's invalid. Okay, so we'll open that up in Ghidra and we'll see how it works and see if we can crack it and make a keygen. So these tutorials I'm recording are in support of Rob Lawry's work with child refugees around Europe in various camps. So if you can support in any way, go and have a look at the link on my description. You can send him some money or you can find out more about what he's doing. And here's a quick video.
Every time I come to camp, I always need a translator, and I always find a really good translator. And today, I found a 13-year-old girl. What's your name?
Banu.
Ban, who's here with a family.
Oh, my name is not Ban.
And
Banu.
Banu?
Yeah.
Okay, I'm sorry. And I'm not going to show her face, but she's here with a family and she's doing all the translating today. I think there's about, how many children here? About 400, 300?
Maybe 200.
200 children in desperate need of shoes. And I can turn the camera around so you can see the camp there. But hey, buddy. But what I'm trying to do is raise money so I can put shoes on these kids. Okay. Hello, friend. You all right?
Hello, I see.
And I put a couple of posts up this morning. Tell them what it's like for a 13-year-old girl to live in the camp. I'm not going to show your face. You can just talk.
There is more than 3,000 people in this camp, and there's 200 kids in this camp who don't have homes. They want to go to London, and there's a man named Mr. Rob. He's helping everybody.
Sure up.
He's bringing shoe stands for people who don't have tents in the camp, and he's so good. He's helping everybody.
Don't talk about me. Talk about what the kids need.
The kids need shoes, clothes, like everything they want. Hats, clothes. They want shoes. For example, there's some kids who don't have shoes, that they need shoes. So Mr. Rob is helping to bring shoes.
You are great. Hey, listen, this girl is 13 years old, speaks absolutely perfect English, and she's my translator while I'm down here for a few days. I've got to know her father and mother really well. They're a beautiful family. So I'm going to put a PayPal address on here. If you can help, I know you always do help me. If you can help, please help. I'm here for a few days and I need to help as many as I can. I know I'm always begging, but thank you. Say bye-bye.
Bye-bye.
And they say thank you.
Thank you for all of you.
Right, let's get this binary open in Ghidra, see if we can figure out how it works, see if we can crack it. So, just as before, we import the binary. This one, confusion.exe. Yep. Okay, let's analyze it. Okay. Right, as before, because we tried the application before, we know that it's kind of a classic kind of serial number scenario. So you type in a username, or you can imagine that's a company name or something, and then there's a license key to go along with that, and you type the license key in, and if the license key is valid, then it lets you run the software. If it's not, then it rejects it. And so it's that kind of CrackMe. So we're going to look in, as ever, we're going to go through strings, see if we can find any strings to find the code that we're interested in. So let's have a look in here. There's just a few things down here. Okay, so input your username. That's usually a good start. So you want to follow the input as it's coming from the user through the application to try and get to the interesting areas you want to look at. So I'm going to go with this one. So input username. So I'm going to find where that string is defined. So you can see here, this is the string in memory, input your username, and it's cross-referenced here, so I'll just click on that and follow the reference. And as ever, we'll go and look in our decompiler view to start with, just to see what Ghidra's managed to do with it. So this is where, yeah, so you can see down here now, so it's saying input your username, and then there's some stuff down here, and then it says input your password here. And if you remember with this application, it's a little bit strange because the password is really a sequence of numbers that you type in. So you type in 11 numbers. So one number, press enter, other number. So it's like a serial number made of different numbers, basically. So we can see it reading that in here. And then there's some stuff down here, which, yeah, it looks like this is doing some computation on the input. So we'll go through that soon. Then there's a check at the end. And it says welcome, make a keygen. So they're suggesting you make a keygen. So that's what we'll try and do. Okay, yeah, so let's just, so we want to be down here. This is where we get it right. You can see down here, this is the wrong path, invalid password, try again. So let's just see if we can figure out what this code is doing and how to crack it. Right, you can see in here as well, which I think was hinted at in the description of the CrackMe, that there's some anti-debugging stuff in here. We'll look at that later. But that often just makes it a bit harder to debug something because it will try and interfere with the debugging. But we're going to be looking at the code anyway statically, so we're not going to. Hopefully, we're not going to need to debug it to be able to crack it. So, right, let's have a look then. So, as ever, it's good to start just naming things. So we're going to say, well, input username here. Now, cout and cin. These are input and output streams. This code looks like it's written in C++. Because of this, it shows us that we're using IO streams. So C++ has its own special, in some ways strange way of handling input and output using streams. It's an abstraction so that you can read from files, you can read from the network, and you can read formatted things like integers or strings. You can deal with strings in different encodings, different like bytes, like you can have sort of 8-bit characters, or you can have 16-bit characters and things like that to represent different languages, so like Unicode and stuff. So it looks like it's using that. So what does that tell us? Well, it looks like this is going to be, where it's reading this thing in here, it looks like this is going to be the username. So we're going to mark that up to make it clearer. So I'm just going to call that username. Okay, and then we can see what happens to that. Okay. Now on Ghidra, there's some useful stuff where you can, well, one of the nicest ways of using it is to click your middle mouse button, if you've got one, on the thing you want to look at. So if I click my middle mouse button on username, it highlights uses of it, which is useful for seeing where that variable is being used in code. You can also do this using these things, so using set highlights. So it's quite nice. So if I middle click on it, I can see where that username is referenced. Okay, so yeah, so this is interesting because like most keygens, the way they usually work is they take the username, they do something to the username, and then they input, they get the serial number from the user, they do something to the serial number, and they check that they match each other. So what we're expecting here is some kind of flow where the username is being transformed. But interestingly, if we follow this username variable, we see that it's only referenced down here again, which is in the stage of this CrackMe where it's already accepted that you've got the right solution. So there's something strange there. So we're going to understand that. Okay, yeah, so let's label up some functions. So this one looks like it's, okay, these are cin and cout are C++ streams, IO streams. I'm going to show you an example of that in a minute, but we'll just rename these things. So we're going to say this is write to stream. Doesn't matter what you call it as long as it's clear. Okay, and this one is reading from a stream because it's reading. Cin is the standard input, the user input from the console. So I'm going to call that read stream. Okay. And we might refine these as we go on if we need to. So we just incrementally try and understand what the code's doing. And if we figure out that some earlier assumption was wrong, then we can adapt it later on. We can change the naming of things. But let's just do this now. So I said before that we can't see this username being followed. And the reason for that is because this is C++. And these, as in other CrackMes that we've looked at before, and probably most common code that you look at, strings are represented by character arrays or just a pointer to a character. In this case, this is C++, and these strings will, especially because they're using IO streams, they're going to be represented by objects. So this is like an introduction to looking at objects, and which are basically structures with functions associated with them. So we're going to try and understand the structure of this because it's not a char star, it's not a character array. This is a string, C++ string. So if we understand how that works, then it will help us follow its use through the code. So that's the fundamental thing we need to figure out now. So, well, let me just find a page to just show you what these look like in C++ if you've not written C++ before. So just 1 second while I find that. Okay, so this is a really nice page that I found somebody's written about just exploring how C++ strings work. And all these things I'll link in the description of the video, so you don't need to worry about that. But yeah, this is, firstly, if we look at this, this is an example of what it looks like when we write in C++ code and we're using strings. So if you want to print a string, rather than saying printf, like we would in C, you take the stream object, in this case cout, which is the output stream, like printf for printing to the terminal, which is actually an object in C. And then we do this operator on it, which actually, that operator actually maps to a function being called on that object. It's just kind of syntactic sugar. And then we're sending, in this case, we're sending size of string, so the string type. So this is actually going to give us some sort of integer or a size t type or something like that, and it's going to send that to the stream, and then it's saying this is the end of the stream. And in this case, this is going to print out a number the size of a string. And if we look at another example down here, you can see that the reason why there's this IO stream abstraction, which has an interesting history. If you look on Wikipedia, you can read about how it was created by, I think, the guy that created C++. And it's also quite complex how it works. We're going to dig into it a bit in this code that we've got to help us understand what the structure of strings are like. But you can see here that you can pass, in this case, it's passing a string out to cout. But earlier we saw them passing an integer out. So it handles things like formatting types. So if you pass it an integer, it will convert that to text and print it out on the screen, just like you would use printf with like formatting symbols and stuff like that. So when a string is defined, it can look like this. So for example, standard string, and then you pass it a character. Okay, so that's how they're defined. So let's go back to our code now. Right. So if this is reading text from the user into the username variable, which we think is a string, let's follow this function and see how it works. Now this function is probably would have been added by the compiler for that operator for reading in a string from the user input stream into a variable, string variable. So we're going to go in there, look at that. Okay. Now this function, we don't need to understand how it's all working, but we're just going to try and use this to understand how we can use Ghidra to help us understand the structures of things. We're doing it from first principles. We could just look it up, but I'm trying to show how you deal with maybe something that you're not quite sure of what it is. So if we look at how this function is called, then what we know is that the first parameter that's called is the stream. The second parameter is the string, which we think is a string object. So let's just rename some stuff. So we're going to call param_rom, we're going to call that stream. Yeah, param2, we're going to call that the string, whatever, string. Okay, which is good. And then, like I said before, if you middle click on that, it will highlight all uses of it. So what do we see in here? So the string, so this function should be reading data into that string. And we can see now that this is not being used. Another example, if we were suspecting this wasn't a char star, when we look at how it's using this function, we can see, for example, it's referencing here, it's saying string index 2, it's setting that to 0. And then it's doing some check here, string 3. So currently it thinks that it's void pointer. So string 3, it's saying if that's less than this value here, which is if I hover over it, it should tell me what it is. 15, yeah. So if it's less than 15, sorry, if that string is greater than 15, then it does something. If it's not, then it doesn't do that. And then there's lots of other stuff going on here. So we're expecting somehow this is reading data from the input stream into that string variable. So a nice thing we can do now is, let's say, so we think this is some sort of object or a structure thing. So if we go on here and we click auto create structure, now it's defined as a structure. It's called a structure, just means just a generic structure that's been defined. And I can see now when it's being referenced that Ghidra is now showing it being used like a structure, which is what we suspect it is, an object with fields. So let's just rename this as, so if I go in here now and I go edit data type, so now I've said the string is a data type, and here we can see it's got some interesting stuff. It knows that it can see that from the analysis, it's figured out that this structure is 32 bytes long, or it seems to be anyway. And that's because it's seen, if this is a structure, it's seen it's being referenced with these offsets. So offset 0 and offset 16 and offset 24 bytes. So it's recognized these as potential fields. Now what we're going to do now, because this looks like standard string, so I'm going to rename it standard string, and I'll click save. Now let's try and figure out, so I'm going to show you some more of that article in a minute, but to start with, let's just try and figure out by looking at how it's being used what's going on here. So for example, we see that first of all this field here is being set to 0, okay, and then there's this thing here that's saying if this field value of string is greater than f, which is also, show that in decimal, 15, then it says this thing, pointer to string, pointer this thing, then points to the value of the first field, so field with offset 0. We can see other, if I middle click on string again, so it highlights it all, we can see here it's referencing these things again, so these things here. Now, if we just look back at that page that I showed you before, okay, so down here there's this part that mentions this thing called small object optimization. Now, the way that we use a string in C is we might either allocate it on the stack with a maximum number, a maximum buffer size, like 100 or something, so we can have 100 characters. Or if that string's going to grow, or we're going to add stuff to it, we might allocate it dynamically so that if it grows, we allocate more memory for it and stuff like that. So that's dynamic allocation. But with a string object, to try and make this stuff easier and to try and optimize certain scenarios, i.e. when we've got small strings, then the actual structure for a string can store a small number of bytes in it. So it's got a small buffer in it. And in this case, it can store, in the case of our code here, we'll see that it can store 15 characters, strings, okay, in the actual string object itself. And if we go over that amount, then it starts to dynamically allocate data that's needed and add characters to that. So the reason it does that is because for small strings, we can avoid allocating memory dynamically. They can just live on the stack. So it's just a optimization, and it's called small object optimization. It's sometimes used in other objects, but we'll see it used in these strings. So what they're doing here in this little experiment on this page is that they're creating strings of different sizes here. And they're finding, so this one was in Visual Studio, they're finding that when they add different number of characters, so they keep adding one character to the string, and they'll see that after they've added 15 characters, when they get to the 16th character, it starts allocating memory. So just keep this in your mind when we look at this code now. So what we have here is, let me find another piece of code I wanted to show to explain this. Okay, so this is just a Stack Overflow question where somebody's asking, why is the size of the string 32? So why is it 32 bytes? So there's a nice explanation here. So if you look at the code for how it's been defined, then we see that the string has, like we said, it's got a small buffer inside it here, so a char star, just like a classic C string buffer, and that can store up to 15 characters. So in fact here. So it also has a capacity that says the current capacity of the buffer, the current buffer in the string, so that we know if this string, if we want to be adding data to this string, we need to know if the current buffer is big enough to hold the extra data that we're going to put in it. And it also has a size. So basically it's got two fields. It's got a capacity field that says how big the current buffer is, and it's got a size field that says how many bytes are being used in that buffer for the actual string. So how long is the string, basically. And the reason there's a union here is because this part of the string can either be a pointer to a buffer if it's bigger than 15 bytes, or it can just be used for the space to hold the internal buffer of 16 bytes. Okay, so that's what the string looks like. So let's just go back to our code. Okay, so now let's start to put some stuff in here. So this one, first of all, if we look down here, there's a check. So here it's saying if string field, this one is greater than 15, then look, it's setting this pointer to the chart buffer of the dynamically allocated data. And that means that if we're less than 15 characters long, then it just points this pointer to the internal buffer of the string, to the start address of the string structure. So we're going to change this now to just say p, we'll call it, as long as we know it's clear, so we'll call it p buffer, pointer to buffer, or pointer to string buffer. Okay, so we can see now that it points to, initially it's assuming that the buffer for the string is the string object itself, but then it does this check and says, but if the string here, this field here in the string is greater than 15, it knows that it's using the actual address of a pointer, the first field of the string, to point to another buffer outside of the string structure that's been allocated dynamically. So this one here, this field here, is the capacity of the string. Okay. When we name all these up, we'll see how the other code that we were looking at before becomes a lot clearer. That's why we're doing this. So if the capacity of the string is greater than 15, it knows that it must be using an allocated buffer because it can't hold that many characters inside the string structure. So then it points the string buffer that it's got a reference later on to this thing, which is, let's call it p external buffer. So we know p external buffer. Good. And so we know that this value where we say this is being initialized to 0, and this is the size of the string. So I'm going to rename that to the size. So this is assuming that our string is empty. So let's have a look at this now. So let's just highlight our string, middle mouse button. So we can see now it's starting to be a bit clearer. So we have the string size equals, now we're not worried about the rest of the code, we're just trying to understand how this data structure for string is being used, because it's going to help us understand how strings are passed around the code that we want to analyze to crack. So string size equals 0 initially, pointed to the string buffer. Initially we assume that it's the string object itself, but then we do this check on the string object to say if the string capacity is greater than 15, then we can't store that many bytes in the internal structure. So it's not a small string. It can't use a small string optimization. So it points it. It uses the first field in the string object as a reference to an external buffer. Okay, so we're basically just using that to decide where the string buffer is based on the capacity of the string. Once we've got that, then the rest of the code can use it. So what do we have here? So when we see the code being used like this, we can rename some of these things. So I'm going to call this one size. I'm going to call this one capacity, because when we start renaming stuff, it makes it a lot easier to see what's going on. Yeah, you can see now. So further down here, it's saying now if size is less than capacity, which we know now means if size is less than capacity. Remember that we're reading the string, we're filling that string up, that username string, with bytes from the keyboard that are being typed in to the application. So it's saying here, if the size of the string is less than the capacity, so if there's still room to add another character onto it, then we go down this path. And you can see here what it's doing. It's saying string size +1, so it's adding 1 to the size of the string because it's reading another byte. Oh, here's the same code again repeated as we saw up there. So this could be generated code, or it could be from a library or something, the IOStream library. But we can see here that it's doing this thing again. So it's working out where the buffer is. It's saying if the capacity is greater than, let's just put that as decimal because it's clearer in this context. It's selecting the string buffer again based on the capacity, which is the same code as up there. Right, so now we can see, if we look what this variable is here, I'll just middle click it, and we can see that this is, so these are functions called on the stream object. So basically they look strange, and this one is just saying, when I said it was a bit complex how it's implemented, these use C++ templates. So all the streams and things, they're defined as templates, and a template just means it's like a structure that's a template for creating an actual real structure. And in this case, we have buffers, so that the IO stream objects, they have common code that can deal with different types. So for example, we can have single byte characters, or we can have multi-byte characters, and all of that stuff. So that's why they're defined as templates. But in this case, this is the one that deals with characters, so 8-bit characters, so just a byte. So it's saying, it's calling a function on the stream sgetC, and if we wanted to look that up, we'd find that that gets a character from the stream. So it's reading a character from the stream, and it returns it here. So let's call this next stream char. Okay, so we can see now it gets that next stream char. It gets it, and all the way down here we see it takes that character and it's adding it onto the buffer. So it increases the size of the string and it adds that next character on. And here, that was when the size is less than capacity. If the size is at capacity, so if the string is already full, its buffer is full, then this is the bit where, to save the developer having to worry about reallocating data when a string grows and shrinks, that's why the IO streams and the C++ framework for strings does this for you. It handles automatic allocation, and that's what it's doing here. So if we're at capacity in the string, then it calls this function, and we'll find in here, if we look in this function and follow it, we'll see a good view for looking at the essence of what a function is doing is, if we go on Windows and we look at function call trees, it shows you the current function I'm looking at. It shows you the functions that led to this function being called, potentially ones that reference this function, and it shows all the functions being referenced by this current function. And I can see things like operator new, memcopy. Yeah, and operator new uses malloc, so allocate memory. So we've got a good idea that this function that we're currently inside of is allocating new space for the buffer. Yeah, because the buffer is not big enough to accommodate any more characters, so it's going to allocate more. So I'm going to call this, just for now, I'll call it allocate new buffer or something like that. That'll do. Right, so if we're at capacity, the reason I'm spending a bit of time on this is because it'll help us to understand in situations where we have similar things, where we've got C++ strings, it's going to help us, but also in cases where we don't know what the data structures are and we need to automatically figure out what they're doing just by looking at the functions that are being called, looking where our where our variable gets passed into and how it gets referenced, what fields does it seem to have, and then you'll start to figure out what certain fields do, and then you might be able to tie that up to a bit of documentation that you've got on that library or something, or a header file, and then you'll say, oh, this is that particular structure, and then you're well on your way. Or you might just figure out a few of the fields, and that might be enough to know how to carry on reversing the rest of the code. So anyway, so it does that, and we can see this is reading stuff into the string. So I think we've understood enough now to go on. Now, if I just, before we go on, if I just right click on here again and edit data type, we'll see that after renaming stuff, our string structure looks like this now. So we've got the pointer to an external buffer, But this is also doubled up for small strings. This space, so 0 all the way down to 15, offset 15, can be used to hold a string of 15 characters long, so a small string with a 0 on the end, I guess. Or it probably doesn't need a 0 because it's got a size in here as well. Or maybe it does, I don't know, but it doesn't matter. But it can hold a string in there. But if the string goes bigger than that number of characters, then it doubles up this first field of the string type to reference an external buffer. And then we've got the size of the string, which is the current length of the string. And then we've got the capacity of the current buffer, which allows us to check if we ever get to the reach capacity in that buffer, then because we've got the capacity stored in this structure, the framework functions can automatically allocate more data, copy bytes across, and then, and I think usually the way they work, without digging too much into that detail, is that if you reach capacity of your buffer, you don't just allocate data for that space plus one, because then you're going to have to allocate it again quite soon. Usually there's some like algorithm like to double it in size or multiply it in size so that you double your buffer size or whatever. Anyway, that's what our structure looks like now. So it's quite the structure editor is really easy to use, and you can adjust it as you go on. You can see exactly what the bytes are used for in your buffer, in your structure, and you can play around with that stuff. So let's close that now. And you're going to see now the benefit of us messing around in this function, which really was kind of a distraction, but let's just go back here. So I'm going to go back to our function, which I think was that one. Here we are. I'm just going to rename this function so we know it's our main check. So we'll call it, I don't know, main app. There we go. Right, now let's have a look at this. Remember before when we looked at this, we couldn't see the username being passed around because we didn't understand the full structure of it. There was other stuff on the stack of this current function that related to that username structure that we didn't recognize as a structure, so we didn't see how it was being used. But now it's going to be clearer because you can see now that in this read stream, it knows that this is a string pointer now, because inside here we said this was a standard string that we defined. So now all we need to do is say that when this reads the username into here, and we now know that this thing here that gets passed into there is a string. So let's just tell Ghidra. So we say retype variable, and we're going to say it's a standard string that we defined here, this one. Okay. Yes. Now look at that. This is where it gets nicer, because you can see now that all of these stat variables are all part of that. They all relate to it. So now it's saying read the username into here, and we've got the external buffer equals 0. Now that's probably was written as null in the code, not 0. So another thing we can do, if we right click on that, we don't really need to do this, but it's useful to know. In Ghidra, there are these things called equates, and equate just means, like you have symbols that point to functions and you can rename symbols and stuff. Well, an equate is just a way of, sometimes you have constants in your code, and in the actual source code they will be referenced as a constant, like like a define or something like that, like null, for example. And null just means 0, but it can make our code easier to read if we mark up some of these things. So I'm going to say set equate for this thing where it says 0. And I'm going to, there's all different ones already defined down here from header files, but I'm going to look for a null. Where's null? There it is, just a normal null. Click OK. And now you can see it's just written null there, which is just useful to know that as you have other constants in structures, then you can start to use these things as well, which is good. You can see now that when my stack is set up in here, this username variable is initialized all to 0. This is probably done in kind of like it's because the string is created on the stack, the string structure, and it will be initialized when it's compiled. It will go in as being initialized like this. So you can see the size of it is going to be 0. Okay. The capacity, interesting, is set to F, which we know from looking at the code, and changes to decimal, is 15. And so when it initializes a string, because it's got nothing in it, it might as well set the capacity to 15 to make sure that it's using the small string buffer initially until it grows. So this is just all initializing our string, and the external buffer is just initialized to 0 as well. That's good. So input the username. So the username comes in here. So now we should be able to follow the use of this username through the code. Now, this is why we didn't see it before being used, because it's actually, if I highlight it again, so username. So the username is used down here in the code, and you can see actually, until it gets to the end, to the success path, it's just referencing the size of the username here, the size field, which is interesting because it means that if we're figuring out how the key gets generated based on the input on the username, it looks like it's just using the size of the username. So if you had Fred and Nick, two different usernames, they would both generate the same code by the looks of this code here. So that's good. So now we can follow that through and we can see what's happening. So what happens next? So we read the username. Now we can see here where it says input your password, because now we can follow the username through the code, and now we want to follow the password through the code. So like I said before, the password, it's interesting on this one because it reads it in as 11 separate pieces of input. And if we look carefully at this function, again, they're a little bit cryptic, but once you're familiar with them, it's not too bad. But this is saying, this function here, it's saying operator, this thing. So this, let's call it in, whatever you want to call it, out, in, for reading in or reading out from stream. So it's reading input from the stream again, like when we read the username, but it's using a different function now. It's not using this same function that read a character string. It's doing this thing here. The interesting parts here are the stream that it's taking. So it's reading from C in stream, but the other parameter that's passed into the function is a pointer to an integer. So this means that what we're doing is we're reading from the input stream, and we're kind of formatting the input from that's been typed in by the user into an integer. So we know now that this puvar5 is a pointer to the password, which it's reading an integer each time, so you have to type in a number each time. So which makes sense if it's a kind of serial number. So let's rename that to p password, and that's a pointer to an integer. This is initialized to this thing here, local 40. And if we look at this, if I middle click it, we'll see what that is. You can see here this is an integer, and if you look, it says here input your password, and you can see from that it's actually checking. In fact, you can see here, if I right click on this loop, say that decimal, these are integers that are iterating through it, and it's reading 11 numbers as part of the password. So, and it's checking here if it's less than 11, it loops around again. So it reads 11 numbers. So we know now that this thing that the password is pointing to, this buffer on our stack, is an integer array of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. This is 11 integers, and this is where it's reading the password into. So let's just update the type of this. So we can do that in here, retype variable, and we can say that this is a 11. There we go. We can call that password or serial number, whatever you want to call it. So if we look at our code now, let's see what we've got. So we have here reading, input your password, we're reading it in, we point a pointer to the password array, and then we're iterating through it, and we see that, yeah, we start the password pointer at the first one, we read it in to there, and then we increment by 1. So the next time we read the password, it goes into the next one. So this is reading the password. That's good. So what have we got now? So now this code is looking a bit clearer, although it's still not exactly clear how it's calculating it. But we've read the password in, and for each integer that is read as the password, so password 0, password 1, password 2, it's doing a check with the size of the username. So it's taking the size of the username. This is XOR, so it's doing an XOR with some other stuff here. So these things. So what are these things? If I highlight one of them, okay, so there's this stuff up here that we've not looked at yet. So there's more stuff on our stack, more variables, and these look like they've been initialized. This looks like a key that's been set up. So let's have a look at how that's being used. So these are all separate, so they're like separate variables. They get referenced down here. We XOR them with the size of the username, and we check if they equal the password that was typed in. And then it's doing something here, and it's incrementing. So this value here is, so if we start from here and work backwards, so this value it's saying if, let's change that to decimal, so 11. So again, it's looking for a match of 11, saying if a total, let's call it, if we call this total, so if total equals 11, then we succeed. If it doesn't, we don't. Which looks like we're checking each element of the password against this XOR with the username and this stuff in the stack here. Yeah, it's not clear exactly how these are, what these look like on the stack. So let's just try and figure out. Right, let's just have a look at this key stuff. So if I click on here, what I'm going to do is open the assembly view as well. I'm going to put that over here so we can see both of them. So this key here, when it gets set up, so these look like they're next to each other on the stack. So they're not really separate variables. They're probably an array of the key. So if we just scroll down to these checks, have a look at the assembly as well. We can see that for each of these, it's indexes them, so 88, 0. So if these are, so these are stored as D word type, so double word, so word is 2 bytes, so 4 bytes. And then this one here, so sometimes Ghidra represent, you'll see things like this concat22, which means take a 2-byte value and join it with another 2, like append it to a 2-byte value, and sometimes it looks a bit confusing. If you look at the actual assembly though over here, you can see that all that's meaning here is that all these other ones are moving a double word, so 4 bytes into the stack pointer, but this one here, it's moving just a double byte, so a word. So it stores it in EAX, and then it stores that into as a word into this value here. But it's just written it like that in the compiler. It's always good to look at the assembly too. Sometimes the assembly is easier to follow. So let's have a look. So if we look at how these are being referenced, so if I take this one in the password checking code down here, we see that, so local 88, whatever that is, we see a word, so 2 bytes gets read from there, and then another 2 bytes gets read from there. So it's using them as words. So we see them stored as a double word, so 4 bytes, but it actually, when it's doing these checks down here, it's just using a word for the check, so half of those bytes. And in the in Ghidra's decompiler, it's done it like this, so we can see like shifts and stuff. And it's just, all this is doing here is it's saying the value that was stored in here, local 88, up here, so this value, rather than comparing the full value, what it does is it right shifts by 10, which is 16. So it's basically chopping off the lower 16 bits. So it's taking in this case it's taking the high word of the byte, and it's doing the XOR with the size there. And you can see here it's doing AND with this mask, so FFFF, which is taking the low word of that byte. So Ghidra has expressed these in shifts and this masking down here, but we actually don't see this in the assembly. The assembly is just dealing with these as word values from each of these, so it's reading a word. So in this case, the Ghidra stuff is actually a little bit more, to me anyway, it looks a bit more confusing than the assembly does. But what it means is that these look like, so these values here, we're setting up here, look like an array of words And if you look at them, how many there are, it looks like there's 11 of them. So let's just clarify, let's just try and tidy up our stack variables to show that. So if I come up here, so this one here, local 88, we're gonna, if we're looking at our function, so function, we can go to edit stack frame. And this just lets us see all of the, how the analyzer in Ghidra picked out all the stuff on the stack, how it's being used. And so this one, 88, local 88, and it looks like, so these ones too, 78, 68, it looks like there in this key there are 11 words. So let's just fix this stack up to represent that. So first of all, I'm just going to clear these because it will complain if I try and overwrite them. So I think it's yeah, if I do clear there, it will make all these bytes now on the stack undefined. Yep. Now I take this one, which was local 88. This is where the first one pointed to. This one. And I'm going to say this is actually, I'll set the data type. It's actually a word, array 11. Yeah, and this is actually, we'll call it the key, because it looks like it's being used as a key. So that's that. Now when you're editing these, you just have to make sure that you click save. Let's have a look at the code now. So now we've got this key. You can see here now it's showing in the decompiled version, it's saying showing the bytes for the key being set up. And these don't look to be done in order. Maybe that's confusers, or maybe that's just how it, yeah, maybe they just set it up in an odd order so it wouldn't, so it looks a bit confusing how they initialize that key. But we can see there the first double word is set up there, then the second there, then this one here, key 10, which is the last one, which will be the 11th word. So now we've expressed that as an array of words, because that's how we saw it being used down here in this check. And this code should look a lot cleaner now. In fact, it does, yeah. So you can see here, let's look at it on the decompiled view as well. See, the decompiled view is using these shifts, which I think makes it look a bit more complicated than it really is. But you can see down here at this code, when it's doing this check, it's saying take the value from key 0, take the size of the username, XOR that with key 0, and check if that equals the password there. So these instructions look a bit odd, and this could have been in a loop, I don't know, this could have been written as a loop and then just optimized or something like that, or it could have been written like this. Anyway, it could have been written in assembly, I don't know. But it's using this thing, move ZX, so this bit is a little bit confusing. So, and in fact, this code makes it a bit clearer actually in this sense. So it's good to use both the decompiled view and the non-decompiled view. But it looks like what happens is, interestingly, so we know that the total has got to equal 11. And so how do we get at that total? Well, it looks like it's doing this XOR checks. It XORs the size with the key, and it checks if that equals the password that was typed in, which was an integer, which makes sense now why you type an integer in. So when it updates the total, it does this thing here where it sets this other var, which I'm going to call, let me just call that total of an underscore. So it's like these two totals, which is just the way the code's been written, I think. But it's, so the first total will equal 1 if it matches. So if the XOR of the size and the key, the first key, key 0, equals the password 0 that was typed in. So for each key value, there's 11 key values and there's 11 password elements, and it's just checking them against each other. Then it increases the total by 1. And here, this is actually a not, yeah, you can see this is a not equal, and it's a bit weird because it's saying if it doesn't equal the thing, then it brings the total back down, so it doesn't honor that last increment of the total. So basically, we can view this as just saying if the XOR of the size and the key at that position is equal to the password, then it increments the count. That's what it's doing here, and it's using these so conditional moves and stuff, which is probably why the Ghidra code looks a bit strange, because it's using these things. But yeah, So just an overview of what's happening so that we can look to crack it. So we read the username in, and we store that in username, which we found was a string object, and then we read the password in, and we read 11 elements of the password, and for each, look, our code is much clearer now anyway. So we've got password 0. It does the check with the XOR of the size and the first element of the key. This masking here is just because it's reading the first word, which we saw in the assembly code view, which is more clear in that sense. So it's checking the first key XOR with username. If it does, increments 1, and it looks like for each one that's correct, it increments it by 1. So if we get a total of 11, then it tells us we've cracked it. So we've got enough stuff there now to try and start writing our key gen, I think. So we'll start with that. So we'll put the key in. We'll start with a username. We'll do this these for the size of the username we type in. We'll make sure that the password matches this, but we'll start building up the code now. Okay, that's good. Right, I've just created a skeleton code for the keygen, so we're going to fill it out now. So we basically pass it a username on the command line, and it should print our code out for us. So I'm just going to run it before we've actually put anything in there, like this. There we go. So let's see if we can make it give us the code. Right, so if we look back at the code, the first thing we're going to do is copy this key into our Python code, so we can, because we need that. So if we look at the assembly view, see, so Ghidra is picked up because of this thing here. So these functions, Ghidra sometimes puts in, it makes up a function just to try and express something if it's struggling to decompile it, if it's struggling to express it otherwise. And in this case, it's not quite clear what's going on there, but if you look at the listing, it's a bit clearer because we can see that it's actually just moving a word, so 2 bytes into key 10. All the other ones look fine on here, they make sense, but this one just looks a bit odd. So anyway, I'm gonna use this the assembly code as a basis. So I'm going to just copy this code here. I'm going to put this into my Python. So first of all, let's just paste it all in here. Right, so let's put them in order to start with. It's going to help. Key 0, key 2, key 6, key 8, there's key 4. And so for key 10, it's just storing this value in there. Right, so I'm going to define this now in here. So we'll call it key equals. Right, I'm just going to move those values up here so I make sure I don't make a mistake. Right, so all I did was I've put these values up here in my key. Now, these keys are words, so they're 2 bytes. And in the code, they get set as a double word here. And we know that the architecture is little endian, which means, all that means is that the very first entry in here is going to be FFB1. The next entry is going to be FF98. Let's just put that up there. There we go. So these are the first. So the first value is going to be FFB1, and then it's going to be FF98. Yep. And we'll do the same for the other ones. And lastly, this one is just a word, so like that. I think I'm typing in Vim. I'm working in Windows because my machine died, so I'm just having to make do. So if I type things like that, then just excuse me. Right, so that's our key. This looks good. So now let's look at the rest of the code. Right, if we just look back at the code now. So what it's doing is it's looping through the password or the key, and it's XORing that the key with the size of the username, and it's checking if that equals the password. To reverse this, all we need to do, because it's XOR, is we need to take the size of the username, so the length of the username, and XOR it with the key, and it should give us this password that we're expecting. So that's all we need to do. So we do that for each character, and if we get all of the password elements are created that way, it should add up to 11 here, and then it should pass the test. So it's a simple algorithm really. So we're just going to loop through our key, and we're going to XOR it with the size of the username, and that should give us our password. Let's try that. Right, so first of all, let's just get the length of the username. We'll just store it in here. Call it L equals length of username. And then the code will create as an array, because we're going to build it up in pieces. Okay, so we're going to build the code up. So all it should be then, if we loop through for key value in self.key, and we'll call it, I don't know, code value equals, and then we just take the value of the key at this position, and we XOR it with the length of the username, and then we add that to the code. So code.append code value, and that should give us our code. So let's just try running that, see if I've made any mistakes. Aha, code. Right, let's try this then. It's going to be no fun typing these numbers in. Let's just make it a bit bigger so I can see my code. Right, let's run it. Continue. Username Nick. Oh no, it's cleared the screen. Right, let me rerun my keygen, and I'll copy this. I've just pasted it into my code. Now let's try the keygen again. The CrackMe. Not that one. Where is it? There it is. So run the CrackMe, and let's try typing these numbers in. So continue. Username Nick. And the last one, 65531. Is it going to work? Ah, said it was wrong. Right, there's something else that we missed, I think, when we looked at the code, so I'm just going to have a look back. I think we're almost there. Don't give up. Right, let's have a look at this code again. Now, go back to the decompile view. So we XOR in the key with the password, that's right, and it's using the size. That's good. We've got the key. Okay, but let's just have a look, because there's something that we missed out here. So we read the username, we set up the key, so the key gets set up. We read the password here. There's this thing here that we've not looked at. So what's this doing here? If we click the middle button on here, see what this is, we can see that this variable is pointing to the key. So I'm going to rename that. I'm going to call it underscore key. So I know it's okay. So what's it doing here? Well, it looks like, if you look at this while loop, it looks like, if we change that to decimal, again, it's looping through 11 items, and it's pointing to the key. So it's looping through the key, and it increments. So this is actually a pointer to the key. So let's just rename that to make it clearer. Pointer to the key. So it starts pointing to the start of the key, and then it gets incremented each time to point to the next element in the key. Yeah, you can see here. So it's doing some transformation of the key. So it's almost like this is the values in input for the key, but then the key is almost like encrypted, and then this code here is decrypting the key before the key gets used. So we've not factored this into our code, so our key is not quite right. It needs decrypting. So how do they do it? So for each element of the key, they take, what's this thing? So what's that? uvar3 initially is equal to 0. So p pointer to key, the value of the key, minus, this is initially 0, and then it becomes the total. So this is like a counter. This is, let's call this I, which is the same as total. Get set to it. So it's an index basically of the key. So it's saying the key gets transformed by taking the value of the key that's encrypted, minus 1 from it, and then XOR it, minus I, so the current position in the key, and then XOR it with the key. Oh, this is negated here, so that means negate it, so invert it. Right, okay, let's have a look. So I'm going to copy this code here, and then the rest is just updating for the index value, but this is where the transformation happens. So I'm going to copy this code into my Python code. Right, so I'm going to create a new function now called encrypted key. What this does is it returns the decrypted key. So let's call it key. We'll write the code for this in a minute. And now instead of directly using the key when we generate our serial code, we're going to instead use self.decrypted key. So now we just need to put that code in here. Right, so this is, I've just pasted in the code from the decompiler. So it's saying for each element in the key, the original key that we put in here, we're going to run it through this, which is take 1 away from the value. So take I, so we're looping through each element. So I would be 0, 1, 2, 3. Take that away from the value of the key, negate it, so invert it, this thing, and then XOR it with the index as well. So let's do that. So we're going to do for I encrypted key value in enumerate self dot key, which is the decrypted key. So we're going to loop through each one, and we're going to say value equals the value of the decrypted key element equals encrypted key value minus I, and then XORed with I. And I forgot I meant to negate this, like that. And that value we're going to add to the decrypted key. And let's just run that, and I've probably done some typo. Okay, so one thing to watch out for in Python is that, see, all these have gone negative now, is that because we have signed integers in Python, so we don't have unsigned integers, we need to basically, when we're doing this, when we're negating a value, if we negate it, it'll become very negative. So what we need to do is just make sure that when we've negated it, that we mask. So if we do ampersand, remember these are all words in the key, so we mask it into 2 bytes. So right, let's print out the key before and after we decrypt it. Just help us see if there's anything else we need to do. So print self key, print key. Okay, so we've got, this is the key before we decrypt it, and this is the key after we decrypt it. And actually all these values fall into, well, let's have a look. I think they're ASCII characters. So if we go back, so if I do for C in key, char of C to print it as text. And let's print that out. Aha, look. So so when we decrypt the key, these values, which look a bit strange to start with, once they've gone through the decryption, it brings them down into the ASCII range, which is why I thought if we do it as if we print them as text, you can see this is the key. Nice one! Exclamation mark. So it looks like we're well onto it now. So now we just need to try this this code in and see if it will bypass the CrackMe. So before I run this, because it's going to clear the screen, I'll just copy these. Bring this back. Okay. At least they're shorter numbers to type in. So I'm going to run it. Continue. Username Nick. Right, first one 74. Second one 109. 103. 97. 75. 106. 97. 37. 41. 91. Last one for. Yes! We did it. Yeah. Yeah, so, well, let's just do a quick recap of what we did. Right, so if we look back at the main function, so we found this one by looking in strings, and we found we were going to follow the input, so we found that this string was input your username. We recognize this as a username variable, which is interesting because we want to follow how it gets processed. But we couldn't see it being used in the function because, in this function, because it turned out that it was a string object, an IOStream string object, C++. So we looked inside this function read stream and we followed it. We looked through how it was being used. We used the Ghidra. Well, it doesn't show it now, but we had auto detect structure thing that we tried, and it found a 32-byte structure. We looked at some of the documentation, a nice blog about strings, which I'll put links to in the details. So we found the structure of a string. We looked at how it's building up the string in here, how it allocates memory if the string buffer's too small, how it uses the string structure itself to store small strings less than 15 bytes long. So that shows all that stuff. And then when we came out of there, we were able to see that, where is it? Let's go back. That username, actually interesting, only the size of username gets used. So in the algorithm, so you could type anything. So Fred would have the same key as Nick in this case. And then we saw the password was being read in, and the password was an integer array. So it's reading integers in using this this function, this IOStream function, to read integers from a stream of text coming from the user from cin. The important part to recognize there was that this was an int type that it was reading the stream into. So it read the password in. We then saw how the password was getting checked against this stuff. But at first, the way this key was being set up wasn't obvious. But we can see that by redefining it on the stack, if I go back to this, where is it? Where is it? Stack. If I go back to here, so if I look on my listing and I look on my stack, if I go function, edit stack frame, remember that I redefined this key part to have 11, it was 11 words, so double byte values. So 11 words was the key, and that made it a bit clearer to see how the key was being used in the code, which was actually clearer when we looked at the assembly, because we can see it's just checking each word in the key, XOR with the size, and that's basically what it was doing, and it was checking if that equaled the password or not for that index. So key 0, password 0, key 1, password 1. So it was quite simple once we got that. And then we started to write it up, our keygen in Python. Where is it? This thing, which I'll share afterwards. So we put the key into there. We got the key. We tried running it, but then we found that it wasn't working, and I had to type in lots of long numbers, which didn't seem right anyway. And it turned out that when we looked more closely at the code, that the key wasn't actually being used directly as it was being set up in here. but it was being decrypted by this function here, which was just XORing it with the index basically and changing it for each index. So it was just a little loop that decrypted that key. Once a key was decrypted, then the rest of it was fine. So it's a good. Sometimes you don't always get it straight away, and you can't try and understand everything because it's just too much stuff to look at. So you just pick away at it a bit at a time until you've got it. And then we found that actually the key then the values for the key looked more reasonable, and they fell into the ASCII range, and actually it was a message that was encoded in the key. So we found that when we printed it out. Where is it? If I run it again, the CrackMe. So the key was actually nice one. It was a string, and it was encoded into there before it was written into the file, into the binary. So yeah, so that was quite good. There's some stuff in here. I'll probably save it for another tutorial. But there's a lot of, when we look in this code, there's a lot of anti-debugger stuff. There's not just this one, but it's called like is debugger present, which is quite obvious, and it's easy to bypass that one. But there's other things in here, so they've put quite a lot of different kinds of debugger checks. There are different things like checking if you're using breakpoints in a debugger to try and figure out a piece of code, then usually more time elapses than under usual use, and so there's checks for checking how much time has elapsed and stuff like that. They use interrupts to try and trigger the debugger when you don't want to trigger a breakpoint, and there's all those kind of things in here which you can look at, but I'll go over that probably in another tutorial. But I hope that was useful. Yeah, thank you very much, and I'll see you next time. Thank you.